Okay, so here is a stress transformation problem, example that we want to do. So our goal here is to determine the state of stress. So that's state of stress is what's this diagram on the left is basically of an element rotated, or this element rotated 30 degrees counterclockwise. So we have on our original element, we have a normal stress in the x direction of negative 75 megapascals because it's compressive. Going in, it's negative. Y normal stress of 40 megapascals and a shear stress in the xy plane of negative 30 megapascals. We know that on this diagram it's negative because if we look at the right, our arrow is going down. So that means it's that's our negative sign convention there. And so what we want to do is figure out, okay, so if we rotated this element, right, if we rotated this 30 degrees counterclockwise, so maybe it looks something like this now, right? And so if we had an original x plane, right, this is original x plane, and we have a new, right, this angle here would be 30 degrees, right, and that's counterclockwise, right? So we have a theta equal to 30 degrees. We want to figure out what our new stresses are going to be on here. So what our new y stress is, what our new shear stress is, and all that stuff. So we have some equations we can use, right? We have some equations we can use here to figure that out. So I wrote out our general stress transformation equations. So we want to find our new sigma x, so that's going to be sigma x prime, our new shear stress, and our new y normal stress. So this isn't a principal stress problem. This is just, we're given some angle that we want to rotate this, and we want to find what our new stresses are going to be. So this problem, we're just going to kind of go through the equations and plug everything in. So to find our new normal stress in the x direction, right? So we're going to want to write out that sigma x prime, right? We have our equation here. So that's going to be sigma x is negative 75 plus 40 divided by 2. And then we're going to have negative 75 minus 40 divided by 2 times the cosine of 2 theta. So if our theta is 30, 2 theta is going to be 60 degrees plus tau xy is negative 30. And that's going to be multiplied by the sine of 2 theta, which again is 60 degrees. So if we do that out, we find that our normal stress in the x direction, our new normal stress in the x direction is going to be negative 72.23 megapascals. So that's just plugging everything into that equation there, and we can find that. We're also going to want to find what our, let's do shear stress first actually. So we're going to want to find what our shear stress is, our new shear stress. So that's going to be tau xy prime. So that's going to be, we have a negative out front here. So it's going to be multiplied. It's be a negative times sigma x is negative 75 minus 40 divided by 2. And that whole thing is times the sine of 60 degrees plus tau xy is negative 30, and that's going to be multiplied by the cosine of 60 degrees. Right, and when we do that out, we're going to get that we have a new shear stress, and that's going to be positive 34.78 megapascals. So we have 2 of these, and we're still going to want to find what our normal stress in the y is going to be. So we're just going to use that equation. I'm going to plug that in. So our y prime. So you kind of notice this is kind of just, this part is the same as the sigma x equation. And then it's kind of like opposite here. It's just kind of like in opposite signs. for this part and then for this part. And that's because that the sigma x and the sigma y are going to be, if we're looking in terms of 2 of the theta, it's going to be 180 degrees away, right? And the actual angle is going to be 90 degrees away, so it's just going to be opposite sides. So we do that again, right? So we're going to have sigma x plus sigma y, so that's going to be negative 75 plus 40 divided by 2 minus negative 75 minus 40, put that in parentheses, divided by 2, right, times the cosine of 60 degrees, because it's still times 2 theta, minus, so it's a minus and negative, so it's going to become a positive, 30 times the sine of 60 degrees. And we do that out, we calculate this, and I calculated this already before I did this video. We're going to get that, that's going to be 37.23 megapascals. So that's going to be positive. So we have a negative x component of normal stress, a positive shear stress, and then a positive y. So if we wanted to go back up here and kind of write what our new thing's going to look like, so we rotate this 30 degrees, right? So we have a sigma 30 degrees. Our new y-x component is going to be negative, so we're going to have these stresses coming into the body, right? And that's going to be negative 72.23. Our y component is going to be positive, so it's going to be coming out. And that's going to be, what was it, 37.23 megapascals. And we have a shear stress that's positive, so that means on the right side, it's going to be going up. So like this, oops, and then an equal and opposite. So I'll just kind of write it over here. So we have a tau xy of 34.78 megapascals. And that's to do our stress transformation. So we went from this, and then we rotated it, and we would go to this new thing, and we can write out what those new stresses are going to be using the equations. So next video, we'll probably just do an example of doing principal stresses, which is going to be finding, now we're going to be finding the angle, right? We'd be wanting to find the angle where the normal stresses are a maximum. So see you next time.